So the set of lecture notes that I distributed you, so this will discuss some key issues in the analysis of non-stationary time series. And first, we begin by looking at different types of non-stationarity. Okay, for example, there could be a time trend, there could be a level shift or a mean shift, there could be a change in the variance, and then the final and most important kind of non-stationarity, there could be a unit root. Okay? Now, the first three deviations, trends, level shifts, and variance changes, they complicate the econometric analysis compared to stationary time series, but we can use the same tools developed for stationary variables and adapt them to these new situations. Okay? However, the presence of unit roots, it changes everything more fundamentally. Okay? So the asymptotic behavior of estimates and test statistics, they all change. So we need a different set of tools for unit root processes, and that's what we will work on in the first couple of weeks. Okay? So let's get started. Okay, so we already defined what we mean by a weakly stationary time series. So the mean and variance are the same, they are constant, and the covariance depends only on the distance. Okay, now if we have two stationary and weakly dependent time series, so forget about what we mean by weakly dependent. If we have two weakly stationary time series, then we can estimate a regression model, the standard regression model, and most of the regression results, they are not different from the IID case. Okay? So here, epsilon t, you could assume it to have no correlation, so it's a white noise process. Even if it's not a white noise process, as long as it is stationary, everything goes through pretty much as normal, asymptotically. Okay? And the reason for that is that the law of large numbers and the central limit theorem, this is what we need to establish, right, asymptotic normality of the standard OLS estimator. Okay, so the central limit theorem works as long as the time series are stationary, and then our OLS estimator will be consistent, asymptotically normally distributed, so you can use the standard inference techniques, right, testing the significance, making a confidence interval, and so on. But the same thing does not hold true for non-stationary time series. So when we are dealing with non-stationary time series, we have to be very, very careful. Okay? And in macro, in finance, this is particularly important because most observed time series, they are not stationary. So what should be done? Well, what should be done depends on what kind of non-stationarity exists in the data. Okay? So time series can be non-stationary in many different ways. And we will look at some of these ways and then discuss how the non-stationary time series should be adjusted and treated in practical applications. Okay? So in some cases, the required modifications to the usual regression tools are minor, and those are the lucky cases, but then presence of a unit root changes everything more fundamentally. You cannot use OLS anymore. Okay? So we need different tools, which we are going to discuss later in the course. Okay, so let's look at different kinds of non-stationarity. We will look at 4 different kinds. Okay. So first, if you look at data, you find macro variables. They often have a time trend. So there is a tendency to systematically increase or decrease over time. So for example, you could think of GDP, consumption, prices, etc. Okay, so I have show you some basic data.
牛逼了，小马哥，我们学校。牛逼了，小马哥。
我观察到老师桌面上他的一组照片。
Okay, so for example, this is a log of the US real GDP, okay, over a long period of time, and you can clearly see a trend in this time series. This is log of US CPI. Again, time trend is apparent. So clearly, these variables are non-stationary. Now, okay, so the trending behavior means the unconditional expectation changes over time. It is not constant anymore, and that violates the first assumption of stationarity. Now, in some cases, the trend is very systematic. That means it's very strong, so that the deviation from the trend is a stationary variable. Okay? So the trend is there, but once you remove the trend, the rest of the variable is stationary. Okay? So if you detrend the variable, that means you remove the trend, then what you are left with is a stationary process, and then the usual theory, usual statistical theory applies. Okay? So a time series that fluctuates in a stationary manner around a deterministic linear trend, we call that a trend stationary process. Okay? So it is not stationary, but the non-stationarity is purely because of a time trend. And if you were to detrend, if you were to remove the time trend, then you would be left with something stationary, and you could use the conventional methods for the stationary part. Okay? So let's think of the following stationary AR1 process. So theta is less than 1 in absolute value, so this process is stationary. And then here is the same process. Using this process xt tilde, you define a new process xt as the stationary process xt tilde plus a constant and a linear time trend. Okay, so because xt tilde is stationary, okay, then xt is going to be stationary around the trending mean. So it's mean value mu0 plus mu1t and plus something stationary. Okay, so we can take a look at this in figure 1a. Okay, so xt tilde, this is stationary AR1. The mean value is 0, so you can see it fluctuates around 0. Then to this xt tilde, you add a constant and a time trend, right? mu0 plus mu1t, then you get this blue line, that is xt. Okay, so this is growing over time, but if you were to remove the trend, you would be left with something stationary. Okay, so that's a stationary and trend stationary process. Is this clear? Okay. Now, the main point of a trend stationary process is that the random or stochastic part is still stationary. Okay, so the random part, the stochastic part, is xt tilde, that is stationary. The non-stationarity is deterministic. Okay, it's not random. This is a constant, and time trend. So the random part is still stationary, non-stationarity is deterministic. So in an empirical analysis, how would you adjust or account for this non-stationarity? Well, you could just detrend the variables by running simple OLS regression. So you have two variables, yt and xt, and you believe they are trend stationary. So remove the trend. Do a regression of y on a constant and a time trend. Then you get the residual from that. Do a regression of x on a constant and time trend. Get the residual from that. Okay? So the detrended variable is going to be the residual. Okay, so that's just going to be yt minus the estimated constant minus the estimated trend, and likewise for xt. So once you estimate the constant and the trend and you subtract it, you get the stationary part or the residual, and then you could run a regression of yt tilde on xt tilde. Okay? Because yt tilde and xt tilde, they are stationary, so we can use simple OLS and then estimate the parameter and test its significance using conventional methods. So that's one way you could deal with a time trend. Okay? Simpler way is you keep the original variables and you just add a time trend in this regression of y on x. So here you don't detrend, you just add a time trend to account for the non-stationarity. So you could do it either way. The two approaches give you identical results. Okay, so what is the cause of linear trends in economic variables? Okay, one is productivity increases over time. Okay, and if changes in productivity are increasing linearly, then that will induce a linear time trend in many time series. Okay, for example, GDP, consumption, etc. And so let's now look at two examples from the real world to understand trend stationarity. So we have here productivity data from Denmark. Okay? So productivity here is measured as real output or real GDP per hour worked. And the data is shown in figure 2a. So let's take a look at this. It's always useful to look at a graph of the data before you do any estimation. Okay? So here, log of Danish productivity, and there is a trend in it. And the interesting thing is, if you look at the deviations from the trend, they seem to be relatively small. So it seems plausible that if we were to remove the time trend, what we would be left with would be something stationary. Okay, good. So just visually, it looks plausible that this variable could be a trend stationary variable. Here we have consumption, log of private consumption, and again there is a trend, but this time you see the deviations from the trend, they seem to be relatively larger. Not just that, but they seem to be relatively persistent as well. So if you are below the trend, you tend to be below the trend for several years. Right? If you are above the trend, then you remain above for several years. So the deviations from the trend are both large and persistent. And that tells us, well, this may not be purely a trend stationary process, maybe something else could be going on over there. Okay, so for productivity, okay, the trend looks very stable. The deviation from the trend looks like a stationary process. So here, the author estimates an AR1 model for productivity, but adds a time trend, okay, to take account of the trend that we saw, and then the autoregressive parameter is, the estimate is 0.56. Okay, so the coefficient 0.56, and seems to be a reasonable fit to the data. Next, we look at the consumption figure. Again, there is a positive trend, but it is less stable and shows large and persistent deviations from the trend. So just by looking at it, it's not clear that the deviations are stationary. Okay, so later we will formally test whether the deviations are stationary or not. But for now, he just estimates an AR2 model. Okay, so later we'll test whether this is stationary or not. Okay. For now, he fits an AR2 model to this data. Okay, so to summarize, if you know that after removing a time trend, you will get something stationary, then we say that this process is trend stationary. And if it is trend stationary, if you have two variables, x and y, which are trend stationary, then you could simply detrend them. Once you detrend them, you can use normal OLS and do estimation and inference. So we can solve the non-stationarity easily if xt is trend stationary. But how do you know that it is actually trend stationary or not? Well, you can look at the thing, but that's not a formal test. Okay, so we will need a formal test, which we will develop soon. Okay, but for now, if you have trend stationarity, that is the cause of non-stationary behavior, that's relatively easy to handle. Okay. A second kind of non-stationarity is a change in the unconditional mean at a given point in time. So, for example, the mean of a time series could be mu1 for the first half of the sample and mu2 for the second half. Okay, so So this is a process with a mean shift or a level shift. So in the first half, you can see the mean is 0 and it fluctuates around 0, looks to be stationary. But in the second half, the process jumps and seems to be fluctuating around 5. So there is a shift in the level or the mean of this time series, and that makes it non-stationary. So what could be a cause of such a change? Okay. So cause of such a change would be some change in the underlying economic structure. Okay. Some institutional change, it could be a policy change. Many things could create this kind of a level shift. Okay. So for example, German reunification, right? East Germany, West Germany, and then they reunite, and that's a shift in the regime. You expect time series to behave differently for unified Germany compared with East and West Germany before the reunification. So how can we handle this kind of non-stationarity? So that's really easy to do it if there's only a change in the mean. How should we address that? Statistically, a dummy variable will take care of this problem. Right? So you can define a dummy variable to be 0 before observation bit t0, and define it to be 1 afterwards, so the break takes place at time t0. Okay? And then you could augment the regression, so you regress y on x, and you add this dummy variable to the regression. So here, only the mean value is changing, okay? But if you think the slope is also changing, then you could also account for that using dummy variable. So the second kind of non-stationarity, a level shift, also relatively easy to fix it using a dummy variable. Then the third kind of non-stationarity is when the variance of the time series is not constant. Okay? So if the variance is not constant, then what happens? So look at figure 1c. So in the first half of the sample, you can see that it's fluctuating within these bands, but in the second half, the variance seems to have become much larger, okay, compared to the first half. So the variance, it seems, is not constant over time, and that violates the definition of stationarity, weak stationarity. So now this turns out to be more challenging from a technical point of view. Okay. And so there is, we use a class of models called arch models or Garch models, different kinds, autoregressive conditional heteroscedasticity models to model the changes in the variance. If we have time, I'll talk about this later in the course. Okay, so then we come to the final type of non-stationarity, which is our focus over here, and that is the one generated by unit roots. And figure 1D illustrates your random walk model. So yt equals yt minus 1 plus an error term. Error is white noise process. Okay, so there we have it. This is a unit root process or a random walk. And how does it differ? By looking at it, can you tell that this is non-stationary? It's not easy, right? Not easy to tell visually. But if you compare it with this, like this variable has a mean, right? It kind of fluctuates around the mean. This variable, obviously the mean is increasing over time, but it's fluctuating around the trend. But here, there is no trend or no constant value around which this is fluctuating. Okay? So for a unit root process, right, for a stationary process, there is an attractor. Right? The mean level is an attractor. That means in the long run, the process can't deviate too much from its mean value. If it's far away from the mean value, in the future it will decline and go back towards the mean value. But in the case of a random walk, there is no mean value to which the process will revert in the long run. Okay, it can just drift anywhere. It could go anywhere. Okay, so one way to look at it is as follows. Suppose you try to create an upper bound and a lower bound for this process. Okay, for a random walk process, for a unit root process. So you set some value, like 1 million and minus 1 million. Okay, very large bounds. No matter what bounds you set, a unit root process will escape those bounds with probability 1 in finite time. Okay, so mathematically you can show, no matter how large the bounds you set for a unit root process, it will escape those bounds almost surely. That means with probability 1 in a finite amount of time. So it's a very volatile process with no stationary or stable value to which it reverts, even in the long run. So it's fundamentally different from any stationary process. Okay, so the random walk has no attractor, wanders arbitrarily far up and down. And these processes seem to be a good description of actual time series. Now, why is this important? Well, for a couple of reasons this is important. One is that now the law of large numbers and the central limit theorem no longer hold when you have a unit root. So that means we cannot use the conventional statistical theory that applies to stationary variables. Okay, so here's an illustration of that using a small Monte Carlo simulation. So suppose we generate an AR1 process like this. The errors are white noise. The initial value is a constant set at 0. Okay, and we simulate the time series n times, and for each block of simulated time series we estimate an AR1 model. So each time we simulate this, we run this regression and estimate theta. So we have a number of estimates of theta, one from each round of simulation. So here they simulate 500 times, okay? 500 observations, and they do 20,000 simulations. Now, what happens to theta hat? Okay, does that converge to its true value? And if so, how quickly does the convergence take place. Okay, so initially the true parameter is set at 0.5, and 0.5, that's smaller than 1, so then the AR process is going to be stationary. Okay, and let's see what happens, the distributions in this case. Okay, so theta is 0.5, and the distribution of the OLS estimator, you can see it is consistent. It is centered at the true value, and moreover, it's nice bell-shaped normal distribution, just what the central limit theorem would predict. Okay, so because this is a stationary variable, then the estimate, the asymptotically, the OLS estimator will converge to a normal distribution. Here is the same thing done when theta equals 1. Okay, that is the unit root non-stationary case. And you can see now that the distribution is skewed, and it's not a normal distribution anymore. Okay, so because this distribution is not a normal distribution, that means the conventional central limit theorems, they don't seem to be working in this case. Okay, however, it's still consistent. It's still centered around 1. Okay, and not just that, but compared to the normal, it seems to be right. See, there is this tail over here, but on the right side, the tail is relatively small compared to the normal distribution. So what that is telling us is, in a way, it's more tightly concentrated around the true value. So the convergence in this case seems to be faster than in the standard case. Okay, so in the presence of a unit root, the distribution is highly skewed compared to the normal, with a long left tail. And so that shows us that the distribution is non-normal, and also the distribution is more condensed compared to the stationary case. And this phenomenon of the distribution being more condensed, that is known as superconsistency. So the convergence speed in the unit root case seems to be much faster than in the standard OLS case. Okay, so now we compare stationary and unit root in more detail. We have already done this to some degree. So AR1 model, okay, and so here we are assuming that theta is smaller than 1, and that means it is stationary. Okay. Stationarity is also described in terms of something called the characteristic polynomial. I'm going to skip this part. We don't really need it for us. Okay. Okay. If you want to know more about this, then you have to read time series book. Okay. So we have a stationary AR1. Theta is smaller than 1. Then by backward recursion, we can express yt as theta to the power of t times the initial value plus a moving average of all the error terms. Now, so we did this earlier, right, before the break? Okay, now, from an economic point of view, okay, this is important because what it's telling us is that a shock has only transitory effects. If theta is smaller than 1, okay, then what that means is that the effect of the shock as time increases goes to 0. Okay, so suppose today a shock hits GDP. There is some shock that increases GDP. Okay, this change in GDP is not going to be a permanent change if GDP is a stationary variable. The effect of this shock will gradually diminish over time. Okay, so if theta is 0.9, the next period, today's impact will be 0.9. Next period, the impact will be reduced to 0.9 squared, which is 0.81. Third period, 0.64, and so on. Okay, whatever. So in this case, shocks have only transitory or temporary effects if theta is smaller than 1. Okay, that's a very important property of a stationary process. Shocks have only temporary effects on variables when the variable is stationary. Okay, that means over time the effect of a shock becomes smaller and smaller, and ultimately asymptotically it disappears. Okay? So we say that the process has an attractor, and if all future shocks were set to 0, then Yt would converge towards that attractor. Okay? The attractor is the mean of the stationary distribution. So there are no further shocks. Today there is a shock, but if there are no further shocks, then slowly the process will go back to the mean. Okay? Of course, in reality, there's always new shocks hitting each period, so you may never go back completely to the mean, but you will go towards the mean asymptotically. So let's look at this figure which shows this idea. Okay.
好想睡觉。你刚刚你睡一会儿。我听了，我闭着眼睛听的。
So here, theta is 0.8, so it is a stationary process. And at time 50, there is a huge shock which hits this process. And you can see the effect of this shock dies out rather quickly in the case of a stationary process. Okay? However, if the process is a unit root process, then, so this is a unit root process, same large shock, but the effect does not die out even after 50 periods. Over here, it never goes back to any mean level. There is no mean level for it to go back to. Okay, so that's a very important difference between stationary and non-stationary from an economic point of view. Okay, so because theta is smaller than 1, and then we show by recursion what this implies is that shocks have transitory or temporary effects. The effect of a shock will decay gradually as long as theta is smaller than 1. But in the unit root case, theta equals 1. And what happens then? So then we have this, yt is yt minus 1 plus epsilon t. And if you do a recursion over here, you replace this with yt minus 2 plus epsilon t minus 1 plus epsilon t, and so on. So you can see that here all the shocks are equally present in today's observation. This shock may have happened in the beginning a long time ago, but it's still present. Its effect is not decaying over time because theta equals 1. Okay? So in the unit root case, shocks have permanent effects. That is a big difference between stationary and unit root from an economic point of view. Okay, in a stationary world, something bad happens today, then you have hope that, in some time it's going to revert back to the old mean level. Okay? But in a non-stationary world, there is no such hope, okay? Because changes are permanent. So that's why it really matters. It's really important to know whether something has a unit root or whether it is stationary, because then we can see whether shocks will have temporary effects or permanent effects. Okay, so an extraordinary large shock increases the stationary process temporarily, but the series will return and fluctuate around the attractor after some periods. Okay, so we can show this we have done already. So the expected value will go to 0 if theta is smaller than 1. Okay, the initial value y0 affects the expectation in small samples, but it vanishes for large t, so that the expectation is 0 in the limit. Likewise, the variance we have shown, if theta is smaller than 1, it will converge to sigma squared over 1 minus theta squared. And you can also derive the autocorrelation function for this stationary process, correlation between yt and yt minus s. And when you do that, you will see that it is theta raised to the power of s. So the correlation or the covariance depends only on s. So that is the third condition for stationarity, right? Constant mean, constant variance. The covariance should depend only on the lag between yt and yt minus s. And that also goes to 0 for large s. It means observations that are very far apart, they are basically independent of each other. Okay, now we compare this stationary case with the unit root. Okay, so theta equals 1, and then we have this random walk model. Now, the solution to this, by solution we mean that you do a backward recursion and express yt in terms of the error terms, the shocks. Okay? So if we do this, then as we just saw, you will get y0 plus the sum of all the shocks. Okay? So big difference between this non-stationary case and the stationary case we saw earlier. So first, the effect of the initial value y0, it stays in the unit root process, does not disappear for increasing t. Whereas in case of the stationary one, you have theta to the power of t y0, that's going to go to 0. So initial value doesn't matter for the stationary case, but it does matter for the unit root non-stationary case. If you take the unconditional expectation, these error terms have 0 mean, so it's just going to be this constant y0 now. So in the unit root case, the initial value plays the role of a constant term. Second, as we mentioned, the shocks to the process, they don't die out. Instead, they accumulate, and that's what we call the random walk component. The random walk component is the sum of all the previous shocks from the beginning up to now. Okay? And so there are different words for it. Some may call it a stochastic trend. Some call it a random walk component. Different ways. Okay? The economic intuition is shocks have permanent effects. That's very important. In the stationary case, shocks don't have permanent effects. In a unit root case, every shock has a permanent effect. Okay, if you look at the variance of this unit root process, then what do you get? So unit root process is this initial value plus the stochastic trend, sum of all the errors. So this is some constant, so it has no variance, and the variance of this is simply going to be, well, each epsilon has sigma square, and there is t of them, so t times sigma square, and they are uncorrelated, so there's no correlation. So you just add up the t variances that are there. So the variance is going to be t times sigma square. And so what that is telling you, the variance is not constant, it depends on time. As time goes by, the variance of the process is increasing, becoming higher and higher. So that's not a stationary process. So the volatility is increasing over time. So clearly non-stationary. Now, if you take the first difference of this process, then you get epsilon t, right? yt minus 1 is epsilon t, and that is stationary. So for a unit root process, if you take the first difference, you get something which is stationary. So because of this, yt is often referred to as integrated of the first order. Okay? Integrated of the first order means that you're integrating these error terms, right? Integrating, you're adding up these error terms in order to get yt. So yt is integrated of the first order. Okay? More generally, a series is integrated of order d if it has d unit roots. That means you have to take the difference d times to convert it into something stationary. If you take the difference once, then you have a unit root process. If you have to take the difference twice to make it stationary, then it's integrated of order 2. If you have to take the difference d times, integrated of order d. Okay? Fortunately, most economic time series, they are integrated of order 1. Some may be integrated of order 2, but that's quite rare. We don't need to worry about higher orders. Okay, so I think we are out of time, so let's stop here for today. Now for the next time, I'm going to show you how to do some tests in eViews. So it would be good if you could bring your notebook, download. Does everyone have eViews on your notebook? No. So you can download a free version, right? There is a free version. That's good enough for this course. So please install that and bring your notebook with you for the next class. Second thing is you need to hand in your group list by next class. Okay, so form your group size 5 to 7 and give me a hard copy of your group list. Okay?
hard copy 是啥意思？写张纸给他。
要我们是的。
不然打开教室，一个人没有，他还一直打走，只有他走了。